Good morning, everyone. Welcome to one of the first full paper sessions. So this session is called Vis and ML, one of those sessions that has Vis and ML in the title. I'm Çağatay Tukay from University of Warwick. I'll be chairing the session. So we have a series of 6 quite interesting talks. 3 of them will be in person, 3 of them will be online. All of these papers involve humans in various stages in the analysis pipeline. We have examples from event sequences to labeling and then to recommendations to all the way with experts working with high resolution images. So it's a really exciting set of papers. So the first talk will be a virtual presentation. And one other thing before switching to that. So we have also online participants. What we suggest is that you put your questions on Slido. There'll be a Slido link on Discord, and then you can find it on the program, on the live stream as well. Make sure that you get your questions while the speakers are sort of going on, and also vote for questions that you like. Right, so we'll start with the first talk of the session. It's on survey on visual analysis of event sequence data. This is a TVCG paper. It will be presented by Yi Guo from Tongji University.
G University. Today I will present our paper, a survey on visual analysis of event sequence data. It's a joint work with Shunan Guo, Jochen Jin, Smitty Kaul, Professor David Gotts, and Professor Nan Cao. Event sequence data are found across a vast array of applications and domains. Discrete observations of different types are collected over time and arranged in sequences based on the specific entity for which the event is germane. In this survey, we review and character visual analytics research for event sequence data. Through the collection and analysis of the 104 literature on this topic, we identify 4 key dimensions of the event sequence visual analytics design space. We then use those dimensions, as well as a characterization of different types of event sequence analysis tasks, to organize existing methods. We collected relevant papers from visualization journals and conferences following 2 main approaches: reference-driven and search-driven selections. For the reference-driven selection, we utilized a core set of state-of-the-art techniques in this topic known to us in advance as a starting point, and extended the range of work by going through cited and citing publications. For the search-driven selection, we went through 2 rounds of paper collection. The first round involves a coarse search from high-impact conferences and journals, then reviewed the abstracts and full texts to finalize our selection. To construct a structured and comprehensive taxonomy, we leverage the conventional visual analytics pipeline that revolves data, model, visualization, and knowledge. To construct our proposed design space, which includes 4 dimensions: data scales, automated sequence analysis, visual representations, and interactions. The dimension data scales identifies what granularity of data the visual analysis aims to cover. The dimension automated sequence analysis identifies the 3 categories of mining and modeling techniques incorporated with visual analytics systems. The dimension visual representations includes the 5 categories of visual representation for displaying event sequence data. The dimension interactions corresponding to 7 interaction techniques that are commonly applied in visual analytics systems for event sequence data. Moreover, as the choices of analysis methods, visual representations, and interactions depend on the analytical tasks and application scenarios. We also extracted the motivating analytical tasks and application domains from each technique. This gives us a full list of 5 categories of analytical tasks and 3 major categories of applications. We explore 9 analytical tasks that are frequently applied to event sequence data, which we further categorize into 5 high-level tasks: summarization, prediction and recommendation, anomaly detection, comparison, and causality analysis. The summarization task uncovers major progression patterns and featuring groupings of sequence entities. A variety of analytical tasks serve the purpose of generating summaries, including clustering, explicit summarization, progression analysis, and inexplicit summarization. The prediction and recommendation are regarding to analyzing observed event sequences to foresee upcoming events or sequences, or examining how certain interventions may affect future trends. The anomaly detection task is corresponding to identifying rare cases that deviate from the majority of sequence progressions. Existing techniques can be categorized by data scales, including anomalous events visualization, anomalous frequent patterns visualization, and anomalous sequences visualization. The comparison task is to investigate similarities and differences between event sequences. Similarly, we classify prior visual comparison techniques based on the granularity of compared targets, including comparison of individual event sequences, comparison of sequential patterns, and comparison of sequence collections. Finally, the causality analysis task is to uncover causal relationships between event types to promote a better understanding of which event is likely to occur after another or of what brings about certain changes to an outcome event. We also introduce application areas where event sequence data are commonly observed. This includes 5 applications, which we further classify into 3 high-level fields: health informatics for electronic medical records, Internet applications for general behavioral data collected from websites and computer systems, and Industry 4.0 for manufacturing data. The record of each patient over the course of a clinical process can be considered as an event sequence, with each event representing a clinical event, such as a diagnostics event, taking lab tests, doing surgery, or taking medicine. We summarize existing visual analytics solutions designed for health records and medical records based on analytical tasks, including cohort analysis, outcome analysis, and prognosis analysis. In various Internet applications, the activities of users and devices can be recorded as individual event sequences. For instance, social media data contains sequences of timestamped activities for specific users that are recorded over time. We provide a review of the visual techniques that have been developed for event sequence data retrieved from social media platforms, e-commerce websites, and computer systems. Industry 4.0 is the ongoing process of using modern smart technology in industrial practices to achieve the automation of traditional manufacturing. The temporal status of smart equipment over time can be recorded as an event sequence, where each event represents a status. A variety of visual techniques have been introduced to help users exploring anomalous events and optimize manufacturing plans. Based on our survey, we found the following remaining challenges in existing research. First of all, the performance of data analysis techniques largely depends on the quality of data. Typical data quality issues include data incompleteness, data errors, and duplication of data records, each of which can mislead statistical analysis results. Moreover, uncertainty is introduced when analyzing event sequence data with quality issues or during user-specified data adjustments. This uncertainty can inhibit analysts from making optimal decisions if information about uncertainty is not properly communicated in the visual analytics process. Scalability is a well-recognized challenge in visual analytics. This problem becomes more significant in visual analytics of event sequence data due to the large scale and high dimensionality of most real-world event sequences datasets. Last but not the least, event sequence data can contain a variety of heterogeneous temporal events. Events of each event type are observed or recorded with different sampling rates and show different event patterns, which leads to great difficulty for aggregating and organizing data from multiple sources. We also found the following promising future research directions. Existing visual analytics techniques for event sequences generally characterize events based on their types and timestamps only. Besides these 2 common event attributes, events in a sequence can also be associated with multivariate data. This implies a need for a new visualization design that is able to represent categorical event types and multivariate attributes at the same time. In the pursuit of better analytical performance, recently developed visual analytics tools tend to leverage advanced machine learning or deep learning models with considerably high complexity. These, however, introduce issues of interpretability of the analysis results and a lack of control over the analytical process, both of which are essential for high-impact analytical tasks. There is a high demand for visual analytics techniques that can organize, transform, and communicate model-level interpretations into comprehensible and actionable guidance. In addition, very few visual analytics techniques have been developed for the causality analysis of event sequences. Despite that some existing visual analytics methods are developed for analyzing multivariate data, the temporal nature and high dimensionality of event sequence data can lead to additional challenges, which are worth addressing in future research. Furthermore, the capability of visual analytics techniques is largely determined by analytic algorithms. In the future study, driven by more powerful deep learning and machine learning techniques, visual analytics techniques could process more complicated data and analytics tasks. This is my presentation. Thanks for your attention. Hi.
Let's thank you again. Hello, can you hear us over there? Hello? Oh yeah, there you are. Thanks for your talk. So we have a few questions on Slido. The first one is about these challenges that you identified and opportunities that you identified. What would you advise us to look into the future? What are some promising future directions? We can't hear you. Is that something on our end? You keep maybe saying a few things and then let's see. No? Okay, Mark is doing something back there. Yeah, no sound. We can't hear you, unfortunately. Okay, we'll wait maybe a few more minutes and then we might have to take the discussion on Discord. Okay. We are solving the problem now. That's our technician saying. But we have to move on. But maybe we move our questions to Discord and we'll have the discussion for you on Discord. Yeah, apologies for this. But then we'll be in touch. I mean, we'll be in discussion on Discord. Let's thank Yi again. So we have another virtual talk, and hopefully by then we'll be in a better position to have the discussions also online. The second paper is called Toward Better Caption Supervision for Object Detection. This is also, again, a TVCG paper. And the presentation will be given by Changjian Chen from Tsinghua University. Hungao, can we switch to the second talk, please? That's Towards Better Caption Supervision.
Hello everyone, I'm Changjian Chen from Tsinghua University. Today I'd like to introduce our work toward better caption supervision for object detection. This is a joint work with Jin, Xiaohan, Shouxin, Songhai, Qifeng, and Shixia. Caption supervision provides an annotation-efficient way to train object detectors since image captions are usually free available. Such methods first extract the object labels from the captions. Then the labels are used as supervision to train detectors. However, the performance is usually poor due to captions are usually noisy and cannot provide precise location information. To address these two issues, there are two challenges. First, the numbers of ejected labels and detected objects are usually very large. Thus, a tool to facilitate efficient exploration is needed. Second, although annotating all the images is expensive, collecting a small number of annotations is more label efficient. How to combine the small number of annotations with captions is still unexplored. In the literature, many methods have been proposed to improve data quality for machine learning. However, as they are not tied to enhancing caption supervision, they cannot be extended to improve the detectors trained on captions directly. To tackle these two challenges, we first propose a node-link-based set visualization to help explore a large number of extracted labels and detected objects. We also developed a semi-supervised object detection method to better utilize a small number of annotations to improve detectors. Based on that, we developed mutual detector to help enhance caption supervision for better performance. This is an overview of mutual detector. Given images with captions and a small number of annotations, a label extractor and an object detector are trained, which are used to extract labels and detect objects. To facilitate the exploration of these results, a co-classing algorithm is applied to cluster labels and images simultaneously. The clustering results are then fed into the node-link set visualization to help users explore the results. During exploration, users can validate the extracted labels and detected objects. The validation is then used to improve the detector. We conducted a case study on COCO dataset. The MAP is improved by 4.8% with only 351 bounding blocks being validated, saving over 93% human efforts. Next, we focus on the first two steps. The analysis starts from the node-link view. In this view, the tree on the left shows the labels. Each node represents a label cluster. The two bars represent its precision and recall. The matrix on the right shows the images. Each row with 10 representative images represents one image cluster. The links between them represent the mismatches between the extracted labels and the detected objects. As we can see, some labels are low in precision and recall. Label cup has the lowest precision. Click it to check words with high contributions in the word cloud. The word restaurant has the highest contribution. Check the captions that contain restaurants. This caption does not mention cups. Its image does not contain cups. Label cup is wrongly extracted from this caption because it contains restaurants. Remove restaurants for extraction of label cup. The experts find that sometimes cup is not extracted from captions whose corresponding images do contain cups. Their captions do not mention the cups in these images. As cups are easily ignored by captions, the label cup extracted from images is added to compensate. Similar to cup, another 15 labels are processed. The performance is improved. Upon update, almost all image clusters are connected with red links, indicating mismatches. The third image cluster has the most red links. 5 of its representative images have undetected objects. Select one image with an undetected bench. The bench occupies almost half of the image but is still not detected. Reduce the confidence threshold, and the bounding box of the bench appears. The bench is successfully located but with low confidence. Bench is correctly extracted from the caption. The bench would be more confidently detected if the detection is more strongly constrained to be consistent with the extracted label. Similar patterns are found in the other 4 images with undetected objects. The mismatches can be reduced globally by increasing the weights of the label consistency constraint. Increasing the weights to 15, the precision, recall, and MAP are improved. After demonstrating the case study, I want to explain the technique details. First, I will introduce the object detection module. Given images, captions, and a small number of annotations, the existing method only uses 2 of them, which leads to suboptimal. To tackle this, we propose a method to combine all of them. For the captions, we extract labels from them as supervision. For annotations, we use them as supervision directly. For images, we ensure that the detected object locations are symmetric when an image is flipped. Experiments show that our method performs better than existing method in all 3 datasets. Then, I introduce the step visualization. In this visualization, to handle a large number of labels and images, we class them such that similar labels or images are classed together. Besides, based on the relationships between labels and images, labels matched with similar images are classed together and vice versa. This can be formulated as multi-type relational co-classing. To conclude our work, we present mutual detector that tightly integrates the object detection method and the interactive visualization to improve detector performance. In the future, there are several directions, like conducting extensive evaluation, improving time efficiency, and study the parameter adjustment. Thanks for your attention. Our codes and video demo are online available. I'm happy to take the questions.
Thank you very much, Changxian, for this really interesting talk. I think it's an excellent example of how to involve humans in the loop. Get your questions on Slido while we wait for other questions. I'll start with one sort of detail that you had on your slide that talked about that you are saving over 93% of human effort. So what's your baseline there? What are you comparing against?
Thanks for the question. In the baseline, we randomly sample some images and ask humans to annotate. And we use the annotated images to train the model to achieve the same performance of the model we get in use our tool. Then we compare the number of annotated images of the baseline and our model.
Okay, thank you. Don't see any other questions, but one other question I had was that the interactions that you have in your interface involved quite deep engagements with the labels, with the text, and with the images. Have you considered how users can be better guided through this process? Have you explored guidance as a question, as a research question?
Yes, we in our tool, user can provide some bounding box labels and adjust the weight of our model. Sometimes in the active interview we conducted with 4 experts, we found that some of the interaction was easy for the users, like providing the bounding box, but some of them is quite difficult, like adjust the weights of the object detection model. We also we also think the how to make the interaction more easily is the future work.
Okay.
Yeah.
Great. Thank you very much. Let's take Changxian again.
Thank you.
Thank you. The next talk is in person, which is great. We have Angelos Chansimperas from Linnaeus University, and he will be presenting the work Feature Envy, Visual Analytics for Feature Engineering using stepwise selection and semi-automatic extraction approaches.
Okay. Hello, everyone. My name is Angelos Chatzibarbas. I'm a PhD candidate at Linnaeus University, and I'm here to present our paper entitled Feature Envy Visual Analytics for Feature Engineering using Stepwise Selection and Semi-Automatic Extraction Approaches. So this talk is in collaboration actually with my colleagues, Rafael Martins, Kostadin Kutzer, and Andreas Keren from Linnaeus and Linköping Universities. This talk will start with a brief discussion of the motivation for our work, and then we have the related research that we found really interesting. Then we describe the visual analytic workflow for performing feature engineering. Afterwards, we present details with regard to the functionalities of Feature Envy, and at the same time, we describe the first use case for the exploration of valuable features. Then we have the presentation of qualitative results of expert interviews that we performed. And finally, I will finish with a discussion of limitations and future work opportunities. Let's start first with a division of the feature engineering, which can be divided into 4 different sub-processes. So we have feature ideation, which is coming up with entirely new features from raw data, and it's completely subjective for most applications. Feature generation is the action of creating useful features from the combination of already existing data. Feature transformation usually denotes less sophisticated modifications over the data. Feature selection is about choosing different subsets from the pool of features that are available by that time. In practice, most of the time spent in machine learning is actually in preparing the features, which should be as concise as possible while retaining vital information about the dataset. Another important reason why feature engineering is quite important is because in real-world problems, it increases the transparency, trustworthiness of the data, and in consequence, it improves also the machine learning process in general. Overall, the complex nature of feature engineering motivated us to really concentrate in this problem. And here we have 3 research questions that we tried to address. A summary of the tools discussed in the related work section and a feature comparison with Feature Envy is presented in this table. A tick indicates that the tool has a corresponding capabilities. Currently, 2 related works focusing on text data support feature selection, feature ideation. However, this sub-process is quite subjective in most applications, especially in text data. Another tool also supports machine learning experts and practitioners in performing exploratory data analysis to understand which transformation they should apply and also what features should be selected. However, it does not support feature generation, and it was employed only on regression problems. Feature Envy adopts the following workflow. The initialization of the feature exploration after the user has split the data into 4 distinct slices sorted by predicted probabilities. The feature selection is a process with 5 automated techniques computed for the choice of features. The feature transformation that enables the user to convert features to impactful alternatives while utilizing statistical measures. The feature generation for the creation of new features from the combination of already existing features. And the tracking of feature changes and analysis of the previous phases using visualizations. while the performance of the current solution is compared to the best result achieved so far. Let's continue with a use case based on the red wine quality dataset. In feature envy, data instances are sorted according to the predicted probability of belonging to the ground truth class. The initial step before the exploration of features is to pre-train the XGBoost algorithm on the original features, and then divide the data space into 4 groups automatically from worst to best. Next, we see the table heatmap view with 5 automatic feature selection techniques, their average contribution, and an action button to exclude any number of features. As we originally trained our machine learning algorithm with all features, the yellow color in the last column symbolizes that all features are included in the current phase. For every method, we normalize the output from 0 to 1 to set a common ground, as indicated in the legend below. At this phase, we want to identify any number of features that can be excluded from the analysis because they contribute slightly to the final outcome. The last 5 features underperform and are having a small influence on the final result. Thus, we choose to remove them. There is still an open question, though. Shall we continue with the removal of features, or should we stop at this point? The core aim of this view is to examine the impact on various subspaces, since removing a feature might appear the right choice globally, but can cause issues for instances in a particular subspace. The radial tree's gray nodes are the 6 remaining features, and perimetrical to them there is a circular bar that starts from 0% and goes up to the maximum, which is 100%, indicating Pearson's correlation with a dependent variable. The light blue to dark blue color is the mutual information computed between each feature and the target. Additionally, the red and green colors in this visualization map the aggregated difference in correlation of a feature if it was transformed at all. At this point, we concentrate on the overall inspection of features for all instances. Feature 4 appears the worst in terms of target correlation because there is a small circular bar and it has one of the lowest mutual informations because it has a light blue color. The graph visualization uses glyphs to encode further details for every feature. The per-target correlation and mutual information are the same as in the radial tree, but an additional horizontal bar charts encode actually the per-class correlation of each feature with different colors. Moreover, there are 4 states that indicate if the variance influence factor per feature was greater than 10, between 10 and 5, between 5 and 2.5, and less than 2.5. Edges are displayed between feature nodes with a correlation above the current threshold with edges with encoding the correlation values. As we proceed with the investigation, we can observe that feature 3, 4, and 6 can cause a concern with regard to collinearity based on the variance influence factor heuristic. Additionally, time per class correlation for all classes is weak. Finally, the correlation between feature 4 and feature 6, or feature 4 and feature 3, can be considered moderate to strong. All those statistical measures lead us to decide to exclude feature 4 from our features list. When the feature transformation is activated, there is a possibility to click a node. This node will expand, exposing all supported transformations which are based on mathematical functions. We compare each feature transformation using the same statistical measurements we described before. After the transformation phase is over, then we also have the feature generation mode, and we can pick 3 features that correlate in a similar way with the individual classes. The selected nodes are highlighted with dark gray color, and the combinations of the different mathematical operations are computed dynamically. From the table heatmap view, we can spot that the first combination contributes much more than the source features. Therefore, we can add the new feature. Each action of the user is actually registered in a punch card visualization. The size of the circle encodes the order of the main actions with larger radii for recent steps. The brown color is used only if the overall performance increases. The grouped bar charts presents the performance based on 3 validation metrics, and also we have the standard deviation due to cross-validation. Teal color encodes that the current action score is better than the results that we have achieved so far in brown color. Two machine learning experts and the visualization researcher actually evaluated our tool in 1-hour interview sessions, and we got feedback about the workflow, the visualization interaction, and limitations. All in all, the experts deemed that feature envy is a useful approach for supporting feature engineering due to the combination of human and computer intelligence. One of the experts mentioned that it could be useful if our system supported custom transformations and generation of features for users to experiment with. Another open issue is that for many features, it would be cognitively cumbersome for a human to explore all these features in different subspaces concurrently. However, we could limit the space of features if we actually have a pre-processing phase in the pipeline. More details about the tool's limitations can be found in the paper. Thank you for your attention, and I'm happy to take any questions.
Thank you very much, Angelos. Really nice work and really nice presentation. Everyone get your questions on Slido. While you're thinking, I have one. And you mentioned that a common challenge in these kinds of analytical processes is to know when to stop. Have you come across some or sort of thought of any proxies to help analysts to know when to stop and be comfortable that, okay, now I can move on with my process?
Yeah, that's a great question. Thank you. So I think if we take a look on the table heat map view that we had a couple of features and automatic selection approaches, right? So basically, you can so if some features could they seem to perform really bad, then really we can very straightforward remove them, and then you can actually stop the process at this point, I guess. But in some cases, there is a case that maybe the feature is like it has borderline values like in between, and then you really want to explore more and continue the exploration in order to transform the features or generate them. So it depends a lot on the first thing, on the first component that we have, the table heat map view. Yeah.
Thank you. And it was that sort of maybe last column with metrics that you use.
Yeah, exactly. Yeah.
Okay.
The combination of the automatic metrics. Yeah.
Thanks, Angelos.
Thank you.
I don't see any questions, so let's thank Angelos again. Oh,
There is a
okay, I'll take it because there are not many questions. I'll use that opportunity. Clarify how particulars of the various possible mathematical transformations is communicated to the user. It seems like they can compare different options, but it's not clear how they would extract the exact nature of the transformation they are selecting from the interface. So how do you clarify or communicate what the data transformation is doing to the features?
Yeah, sure. Thank you for the question. So data transformation, we actually have, like in the paper, we mean that it's typically, mathematical functions like, you use a logarithm in the data, or you bin the data. So this kind of this is what we call transformations in the paper. And generation, we typically mean when you combine really with mathematical functions like subtraction and addition. So this is like a generation of features because you combine two of them, right? So basically, transformation is when, when the distribution is shifted, then you typically want to maybe use logarithmic transformation, to have this normal distribution or something like that.
Okay,
Yeah.
Thank you.
Yeah.
And I think part of it is really communicating some of those complications of these transformations.
Yeah.
So maybe you can take this discussion also on Discord.
Yeah, I
So
would do.
let's thank Angelos once again.
Thank you.
Our next talk will be, it's listed as in person, but it will be virtual. So it will be delivered by Jilan Chu from University of North Carolina, Chapel Hill. And it's titled A Design Space for Surfacing Content Recommendations in Visual Analytics Platforms. So let's hear Jilan.
Today, I will introduce our work, a design space for surfacing content recommendations in visual analytic platforms. A joint work with Wenyuan Wang, Mengtian Guo, Yue Wang, and David Gotts from the University of North Carolina at Chapel Hill. Content recommendation systems are used widely on websites such as search engines or shopping websites to recommend related documents to read or related products to purchase. They are also widely used on online social media platforms to recommend videos, posts, and other content, based on both users' current interactive activity and models of users' historical preference. On visual analytic platforms, content recommendations are used to recommend information like related data to users. The recommended content could be highlighted data points or new related information. The goal is to help users more effectively identify new information that is relevant to their analytic context. Our work is a literature review on the state of art in how visualization systems surface recommended content to users during users' visual analysis. Especially, we focus on how recommended content is surfaced to users during visual analysis. We also present a four-dimensional design space to describe visual content recommendations. We want to point out the differences between the form and the content recommendation here. Given an input data set and perhaps some additional information about the user's task or preferences, form recommendation systems recommend one or more views of the input data, while content recommendation provides recommendations of new content that should be brought to the user's attention. Form recommendation systems suggest one or more views of the input data, while content recommendation systems provide new content to users. We follow the search strategy and screening process specified in the PRISMA standard. PRISMA defines a multi-stage procedure that has been widely adopted in health and medical fields for systematic literature reviews. We identified articles from both IEEE Explore and the ACM Digital Library. We used the keyword adaptive visualization to get candidate articles. In total, 175 articles were identified via the specified keywords. A screening process was followed to remove duplicates and exclude irrelevant articles by examining titles and abstracts. The 92 articles that emerged from the screening process were then inspected more closely for eligibility via a full text assessment. This step ensured that papers which appeared relevant from the title and abstract screening were indeed appropriate for inclusion based on the research topic. We then applied additional eligibility constraints to exclude more papers that did not present a working prototype with user interaction descriptions. This is to ensure that our survey focused on designs that were used in actual implementation from prior work. Finally, we removed 6 papers where the prototypes were deemed not relevant to the scope of the study or were identified as duplicates that describe the same prototypes as other papers in our collection. These steps reduced the included set to 17 papers. Recognizing the limitations of keyword search, we enriched the collections of relevant documents by examining all citations from the 17 papers from the last step. Every reference went through the same screening and eligibility steps as the original candidate articles. More details are reported in our paper. The final set of 26 publications that were included in the survey were then analyzed by the authors to extract details regarding the ways in which the described prototypes surfaced the recommended content to users. Descriptors of various techniques used in prototype systems were recorded following an open coding process. The descriptors were iteratively refined and grouped to identify the key aspects that could be used to characterize various design choices. At the end of this process, the descriptors eventually consolidated into the 4-dimensional design space: directness, forcefulness, stability, and granularity. The directness dimension describes the relationship between where a user is interacting with visualization and the location at which recommended content is surfaced. If the user is interacting with the scatter plot, a direct recommendation is in the same plot, while an indirect recommendation is under a different tab. The fourth one is dimension represents how intrusively the recommendation is surfaced with respect to the user's workflow. Fourth one is assessed on a 5-point scale, with 1 being the least forceful and 5 being the most forceful. Here, recommendation under another tab is ranked as level 1. However, this pop-up window is ranked as level 5. The stability dimension describes the temporal dynamics of when the content being recommended is updating within the interface. Design choices within the stability dimension can be classified into 3 general categories: periodic, event-driven, and on-demand. The granularity dimension describes the relationship between the unit of content that a user is interacting with and the unit of content being recommended. Imagine the visualization is showing the relationship between the wholesale and market prices of orange. If the system recommends information about the prices of citrus fruits, we consider this a coarser granularity recommendation because orange is a narrower concept than the citrus fruit category. We use the design space to categorize each of the 26 papers identified in the literature review. The findings are reported by dimension, with the full results summarized in this table. Details could be found in our paper. For trends across dimensions, we observe the relationship between forcefulness and stability, in which designs with higher levels of forcefulness had more stable update policies. Similarly, we found an apparent link between systems that offer recommendations with varied granularity with more stable on-demand designs. Please check more details in our paper. Opportunities. The results show that some areas of the design space are underexplored, such as low forcefulness designs and designs with periodic updates. While this paper has focused on the visual display of recommended content, future studies examine design decisions for the underlying models and algorithms that support content recommendation could be valuable. Thanks for listening.
Thank you very much, Zilan. Let's hope that you are with us and can hear us and can also speak.
Yes.
Perfect. Everyone get your questions on Slido. When we wait for more questions, I had a question around the methodology that you applied. I mean, I know Prisma from papers in the health domain, as you mentioned. It's a very rigorous methodology, which is quite unusual in the visualization literature. So how was your experience using it? Do you think that will be a standard for state-of-the-art reviews in visualization?
Thanks for pointing that out. So as we mentioned in our paper, the Prisma is widely used in the healthcare, but not really for the visualization. I think for the whole computer science society, we really is not that familiar to this method. And it is a systematic method that we could search from the very basic, and the procedure could help us from the search to the eligibility and screening and all those by following those procedures, we could clearly to explain how we get the set of our data, and for all the survey to it's kind of to prove that our survey is comprehensive enough to state the current just for the any kind of research questions. So yeah, the experience is pretty smooth, and they already have a really heavy a bunch of pages of the instructions for how to do that.
Mm-hmm.
For the future of how the visualization society will use it, I'm not that sure, as like, yeah, it's more like a tradition for the healthcare, the society to use that. But here, like, there are several papers, like several survey papers here in this section and other, like in this Vis conference, and we see like all people use different kind of methods. So I would like to say that probably someone could to help to do something similar here, help like later for other people doing the survey papers that they could follow some kind of standard and help others to read it quicker and to get the idea more smooth. Yeah. Thank you.
Excellent. Thanks. Let's see how that goes. There's one more question, but we are running a bit late. So if you can take that question on Discord, Jilan, that would be great. So let's take Jilan once again.
Thank you.
Our next talk will be in person and will be delivered by Yishuan Li from Fudan University, and it's the title of the presentation is Diverse Interaction Recommendation for Public Users Exploring Multi-View Visualization Using Deep Learning. So it's a very interesting, very different paper. Sheila.
Good morning, I'm Yishan Li. Well, this is my first visit here and, oops, excuse me? Yeah, sorry. Yeah, this is my first visit here and I feel quite honored to present the work, Diverse Interaction Recommendation for Public Users. I think might be the connections are quite stable here. Yeah, I'll play here. I think it's better, yeah. So today I'm here to present the work. Yeah. Well, I've said the title for several times, but yeah, this is a collaborative work with Yusheng Qi and Siming Chen from Fudan University, and Qingchen Yang Shi and Nan Cao from Tongji University. And I'm now with University of California, Santa Barbara. So visualization system has been recently introduced in public cultural centers, museums, and websites, accessible via touchscreens, computers, and mobile phones for public education tasks. In the past 10 years, researchers have made considerable efforts to create large and advanced visualization systems for audience to browse and explore, such as M-Dialog, DeepTree, and Living Liquids as shown here, which are the more important foundations of museum visualizations. However, visualization systems constructed of multiple linked view and interaction types are often complicated. Which interaction to operate and which part of data to explore are hard questions for public users. Making these decisions largely relies on professional experience and analytic abilities, which is a huge challenge for non-professionals. Through our interviews and literature studies, we concluded that users feel hard to construct interactions in visualization systems without proper guidance and instructions. So facilitating users' exploration in the visualization systems has become a significant priority. While most of the current research is limited to single-view visualization systems or consider users' one-step interaction, which is unable to support visualization systems with multiple views and interaction types. So in this work, we provided a solution that targeting the above challenge. We're primarily focusing on designing a model to generate interaction recommendations for public users. To be more specific, the following discussion is set within the museum scenario, but we also argue that the pipeline can be generalized into different visualizations under these scenarios. So public users here are defined as regular museum visitors with different background, has little knowledge about the topic and data analysis, but are curious to explore more for the insights. The provided interaction recommendations should satisfy the following requirements. Real time, when users face the visualization system, we believe the most straightforward way is to provide recommendations right after one interaction is made. Diverse, the recommendations should support a cross-view and various types of interaction. This can help users conduct more in-depth explorations and help the system be fully utilized. Insightful, the system should offer insightful interaction recommendations that lead to valuable explorations and deepen the user's understanding about the topic she explores. The model performs as an end-to-end pipeline with users' previous interaction logs and visual states as the input and the recommendations of the next step as the output. In the user's workflow, each time a user makes one interaction, the system will collect the interaction and visual states and then transform them into numerical vectors. In the predicting workflow, the pre-trained models receive the data and output the predicted vectors. After being converted into the JSON data structure, the recommended interactions will be sent back. So we developed a taxonomy of interaction logs based on the previous methods. Then the encoded interaction logs will be divided into 4 parts that can define one unique interaction form from the interaction types we considered. The user's interaction is recorded and converted to the JSON format. We then apply an embedding method using the context-free grammar representation. Then to the multidimensional vectors. So for instance, here in this example, the user performed a brushing on the map view. So we collect the brushing and the map view and also the corresponding coordinates of where the brushing bounding box is, and then convert it to the tree format, then to the numerical vectors. We also compared several sequence analysis models and found that the LSTM model shows significant advantages under this task because it considers users' historical interaction data and mimicking users' cognition ability and is easier to set up. So the model captured key embeddings of previous interaction logs and visual states and output the interaction embeddings of the next step exploration. Instead of using a static model, we divided the model parts into 2 parts. The training part cleaned the collected data using 2 filters of diversity and insightfulness to ensure the data quality. We compute the entropy of users' interaction to measure the degree of diversity and keep the interaction log only if the entropy is higher than a threshold. And an interaction is insightful if it involves interaction within the insightful data area we define. And the continuous learning part we achieve by when a user rejects one interaction, we collect the actual interaction and use the collected data to continuously fine-tune the model to improve the performance. This example shows one time of interaction recommendations. So the model captured these interaction logs and returned the different recommendations as highlighted in this chart. We can see there's highlighted bars here, and it reflects the concept of mixed initiative in our method. And we also propose an interactive visualization system in the museum scenario as an example to implement and test the pipeline. The 4 different points from Song Dynasty are selected. The data consists of temporal trajectory data of when and where a literature was created and its content. 7 different interaction logs types are encoded based on the different views in the system as listed here, and we also obtain the corresponding visual states and transform them into low-dimensional data. And the training data was collected from 47 participants. More than 4,000 interaction log vectors are collected. The training duration, the accuracy, the loss value, the mean square errors are compared, and 3 models within the best prediction performance are selected. Also, we create an ambient experiment to evaluate the performance of the weighted filters and also the model updating. We can see from the table that the filters improve the degree of diversity and degree of insightfulness, and also the model updating increased the model's predicting accuracy. This video clip will show how the system works. There's no audios here. No, I don't think so. Can you hear from here?
Based on the background information, we know that Su Shi was born in Sichuan province and spent the last years in his life in the southern part of China. Therefore, we start our exploration in Sichuan province. We first zoom in and click on the marks on the map view for browsing. After a while, the system starts to provide recommendations for us. We follow its suggestions and gradually be away from his hometown and approach to Kaifeng, the capital of the dynasty at that time. The system inspired us to brush the area around Kaifeng for a deeper investigation. With its suggestions, we clicked Huaiyin, Weishi, and Kaifeng on the force-directed view and discovered their locations on the map. The system later suggested us to explore the histogram to see his journey in a certain period of time and his creation. After that, the system led us to explore the south step by step, based on the given recommendation.
We further conducted a control user study and in-depth interviews for evaluation. Please find more details in our paper. So this work involves trade-off relationships in many aspects and need to be further considered. First, the balancing between diversity and insightfulness determines the weight of 2 filters. Second, whether we should keep the presented information clean and concise or provide more exploration of why these interactions are made should also worth discussion. Thirdly, there are differences between providing recommendations to public users or professionals. And also, we would like to compact our method into a toolkit that can be added into the existing visualization system to improve the generability. So what we can take away from all of this, including for following 3 aspects. First, we propose a method that models interaction logs from different views and interaction types into vectors that share the same structure. Second, we propose a mixed initiative approach for across view and interaction types recommendations, and can provide real-time, diverse, and insightful recommendations. Thirdly, our approach is proven to effectively help public users gain more knowledge in the public education scenarios, thereby improving the accessibility. For more information about technical details, case studies, and evaluation, please take a look at our paper. Thank you, and welcome all the questions. Thank you.
Thank you very much, Ishuan. Really interesting work. So there are lots of questions on Slido, which is great. One that got lots of support is about involving experts in the data collection process. One concern was that if your model uses public data or so public interactions, can that create an issue of trust, and or would involving expert interactions improve your models?
Yeah, I think that would be a great suggestion. So now the collecting data part we invite more of the public users as the data collecting. And the way we did this is based on the practical consideration. So when this system or the pipeline implemented in a real museum scenarios, it's going to be very hard to pre-collect a lot of data from the users and implement it here. So the way we did this is while the users continuously learning using the system, we collect their data and in this loop we also regard this as a data collecting process and use the data collected during the actual use of the public users and use the data as a training data. So yeah, I agree that involving expert users in the data collecting part will help to improve the recommendation accuracy or also diversity and insightfulness. But yeah, the current way is more based on how the system and how this pipeline can be implemented in the actual using process. Yeah, thank you.
Thank you. We are a bit late, but if you can give a very quick response, because there's this discussion going on slide on insightfulness. How do you define it? It's a metric. Can you say a few words about it very quickly?
Yes, so the diversity and insightfulness we defined is as a quantitatively method. So the diversity we define is when the entropy of the interaction is larger than a threshold, and the insightful interaction we define is we do a pre-analysis of the data set and define some insightful area that based on the data distribution on the interactive system. So if the interaction lies within this insightful area, we define this as an insightful interaction.
Excellent, really interesting. There'll be more on Discord, so if you're on Discord,
Sure,
you can
I'll
take those
take a
questions.
look. Thank you for your question.
Thank you very much, Yichuan. Yes, thank you. So our next speaker is also in person. So the next talk will be given by Simon Warshall from Harvard University. And the title of the talk is Vicinity Visual Spatial Neighborhood Analysis for Multiplex Tissue Imaging. Simon, the floor is yours.
Fantastic. Hello, I'm Simon Warshall. I'm a PhD student at Harvard University, and today I'll present our project Vicinity, Visual Spatial Neighborhood Analysis for Multiplex Tissue Imaging Data. So, over the last 10 years, advances in tissue imaging have allowed pathologists and cell biologists to investigate cancer tissue at an unprecedented level of detail. And these advances, namely whole slide imaging, have allowed us to scan and digitize large regions of tissues and analyze them computationally as well. And so with this new data, experts now seek to understand the tumor microenvironment, both in terms of the cells it's composed of and how those cells may be interacting. And one way to study these interactions is through something called spatial neighborhood analysis, which looks to see which cells neighbor each other as a way of identifying interaction patterns. And these neighborhoods and patterns can exist at multiple scales, so between cells directly next to each other or across broader regions of tissue. And overall, the goal of experts here is to use these patterns to identify specific biological structures and processes that might correlate with the progression of disease or response of cancer to specific treatments. However, investigating spatial neighborhoods in this new data has a number of challenges. First of all, the data is very big. The data that our collaborators work with contains millions of cells, 30 or more channels, each reflecting the expression of a different biomarker, and also contains an accompanying segmentation mask and a single cell table reflecting the marker expression value and cell type of each cell in the data set. And what we found is that what few existing approaches to spatial neighborhood analysis and tissue imaging data did exist were intended for imaging modalities containing thousands and not millions of cells. They simply did not scale. And to add another order of magnitude to this, then, we found that our collaborators weren't just interested in looking at single tissues in isolation, but they wanted to look across cohorts of 10 or more tissues. And additionally then, through close collaboration with some domain experts at the top of our field, we found that the needs from expert to expert were very disparate. Some were interested in more exploratory workflows, whereas others were interested in performing confirmatory analysis. And we couldn't really find existing approaches that could accommodate this. And finally, a big point of emphasis from our collaborators is that these experts must be in the loop. They have years of experience studying tissues. They know so much about the biological significance of tissues and the interactions it might contain, so they really need to be able to steer analysis and verify results interactively. So based on these challenges then, we formed a working group with experts at the Lab of Systems Pharmacology at Harvard Medical School and the Santagata Lab at Brigham and Women's Hospital. And from this working group, we propose an interactive workflow for spatial neighborhood analysis. And this workflow begins by quantifying the neighborhoods of each cell in a specimen and across specimens in a cohort. So the user will specify the size of neighborhoods they want to investigate based on the radius, and then we identify all cells within that distance of a given cell, and based on the cell types in that region, we form a neighborhood vector representing the weighted number of cells of given types in that neighborhood. And if we repeat this then for every cell in a specimen and across all specimens in a cohort, what we find is that patterns emerge. So cells with similar neighborhood vectors represent cells with similar spatial neighborhoods. So once we've quantified these neighborhoods, which kind of serve as the backbone for a lot of our analysis, a user then will move on to browsing all of the tissues in their cohort. And I'll now show the system we designed, which is called Vicinity. So a user begins with an overview of all the tissues in their cohort. They can zoom and pan around the tissues to get an idea of their morphology. And if they're interested then in investigating in a little bit more detail, they can dig into an individual tissue and investigate further. So once they've then looked at a specific tissue and they want to investigate the spatial neighborhoods in that tissue, our workflow supports both bottom-up and top-down analysis. And I'll start with just bottom-up analysis. So a user can zoom and pan around the image and select regions of interest. And when they do so, the cell types in that region are highlighted with color-coded outlines. And to provide a little bit more context as to the neighborhoods in a selected region, we visualize the composition of these neighborhoods as a parallel coordinates plot, which shows the composition of neighborhoods in a selected region and also optionally in the entire specimen or cohort. We embed these neighborhood vectors into 2 dimensions using UMAP, which we visualize with an interactive scatter plot. And here we find that points next to each other then represent cells with similar spatial neighborhoods. And they can zoom and pan around that and select regions in the scatter plot, which then visualize where in the tissue those neighborhoods exist, as well as in the other linked views. And finally, we use an interactive correlation matrix to encode pairwise correlation between cell types in neighborhoods, again, both in the selected region and in the overall specimen or tissue. Now, when a user wants to detect patterns in a data set that includes millions of cells, we also wanted to provide some sort of semi-automated means. And so to do so, we allow users to cluster the neighborhoods in a specimen or across specimens in a cohort. To do that, they simply input a number of clusters, and then those clusters will just pop up right below, and they can just toggle through them to see where they exist both spatially as well as in the linked views. And if they notice a specific biological structure or biological process that's been captured by this cluster, they can label it and save it for further analysis. So through this bottom-down analysis, users can explore and generate hypotheses. We also then support top-down analysis through 2 forms of visual querying, where users can look for neighborhoods and refine and test hypotheses. And to get into that, first, what we found is that a lot of our collaborators are interested in looking at particular interactions between cells. And so to do so, if they want to do that, they can simply sketch out an interaction in the composition view and then search for it, which will reveal matching neighborhoods, again, across the tissue and in the linked views. Next, users can search by example. So say they find an interesting structure within the tissue itself, they can select it and then search to reveal similar regions that have similar neighborhoods across the tissue. And moreover, this search, as well as all the other features I've shown, are not simply limited to a single tissue, but also work across cohorts. So they can pull up this side view here to see where matching neighborhoods exist across all the tissues in their cohort. And here we show all the matching neighborhoods in all the tissues in the cohort, and they can sort them based on how many matching neighborhoods exist, as well as the statistical significance of that pattern in the neighborhood. So throughout analysis then, experts are saving and labeling and annotating things that they find that are interesting. And we also want to allow them then to compare their findings and summarize them. And so to do so then, in that same right-hand side view with the cohort results, we also show small multiples visualizing the spatial context of every pattern they've saved and labeled, as well as we visualize the composition of each of these saved and labeled patterns as small multiples of bar charts to give a quick representation of what these neighborhoods contain. To evaluate vicinity, we held 2 case studies with domain experts. I won't go into the first one, but I'll highly encourage you to read the paper. But I'll quickly just go through the second case study. And this case study was conducted with a cancer biologist at the Santa Gata lab at Brigham and Women's Hospital. And here we're investigating 10 specimens of cancerous mouse lung. And of these 10 specimens, 5 are genetically engineered to have a robust immune response, and 5 are genetically engineered to have a poor immune response. And the goal here then of this expert was to identify immune structures that might exist within this cohort and see maybe how it differs between these 2 types. And what we found actually is that by exploring the embedding space, we found 2 distinct regions in the embedding space corresponding to immune structures of note. The first of which was richer in helper T cells. And when we investigated it then within the individual images, we found that this corresponded to immune structures that were located directly outside of tumors, as well as some structures that were very distant from tumors. And our collaborators were particularly interested in those distant structures, which they thought might be the precursors to immune structures called tertiary lymphoid structures. The second then interesting region in the embedding space we found, which was richers in B cell and particularly present in the immune-rich cohort, we found represented tumors which were infiltrated with immune cells. So here the immune cells were actively fighting the tumor. And I'll just note that these 2 structures are actually a key takeaway of an ongoing publication with the Santa Gata lab at Brigham and Women's Hospital, which is currently under review. So they use vicinity essentially to help identify these structures. So then to quickly conclude, what I've presented here is this human-in-the-loop workflow that we developed in close collaboration with experts at the top of their field, a scalable computational pipeline to quantify the neighborhoods in a specimen or across specimens, as well as vicinity, this visual analytics system, which supports all this analysis. I'll also note that we have some more evaluation of the system in the paper. We evaluate each of the individual features with a larger group of experts and also show some scalability evaluation of the individual features we offer. With that, I'd just like to acknowledge all the everybody who supported this research and my other members of the Visual Computing Group and Lab of Systems Pharmacology. I'd like to specifically thank all the co-authors on this paper, I guess specifically the co-first author, Robert Kruger, and my advisor, Hans-Peter Fisser, both of whom are at Viz today. And yeah, I would encourage you to scan the QR code to try out the repository. We have sample data sets, executables for Mac and Windows, and would love to hear from you. I'd love to have anybody test it out. Thank you so much.
Thank you very much, Simon. Really amazing work, and the same comment is also on the slider. The first question is about 2D, 3D. So the examples the case studies are on 2D images. Do you think how this could extend to 3D volumetric data, and then how it will impact the interactions?
Yeah, so I guess we're just actually starting to get some high quality 3D data. I think the difference between those data sets is that the 2-dimensional data that our collaborators work with is really, really big. It is microns in size, whereas the 3D volumes are a lot smaller. But I think basically all of the methods would more or less translate if we just look in 3 dimensions, in a sphere around each cell as opposed to in 2 dimensions. But yeah, that's definitely a topic for future work. And actually we have some members in our group that are currently kind of looking into how we can investigate those patterns in 3 dimensions.
That's excellent. And one question I was having, so you really nicely presented the top-down, bottom-up analysis approaches. Have you noticed any preference to what your collaborators prefer the most?
Yeah, I think our collaborators were, particularly interested in the top-down analysis, actually. I think that they spent a lot of time, investigating tissues, a lot of time zooming and panning through individual tissues, and often find things that they want to say, okay, this structure I found, does it exist anywhere else? And so the ability then to kind of search across visually on multiple tissues, I think was particularly something that they're interested in, yeah.
Excellent. Thank you very much. There are a few other questions, but they'll be on Discord. If you can take them over there, it'll be great. Thank you very much, Simon.
Thank you, everybody.
I know we are a few minutes into the coffee break already, but I want to give our first speaker the chance. I don't know, Mark, can we, if it's working now, can we get the first speaker to at least respond to the question that he was asked? Can we get him up? Yi, can you hear us over there? I don't know if you are still online. I wasn't able to reach you. Okay. Looks like he's having a coffee. All right. Thank you very much, everyone, for... No. Okay. Thank you very much, everyone, for your questions and for your contributions. It's been a great session, and enjoy your coffee. And there will be another, I think, VA-ML session in this room in the following. Thanks.